Hey, AP Chemistry. Today we're going to talk about molecular polarity for a little bit, and it's kind of an exciting topic because it takes a lot of what we've been talking about and kind of culminates it in one purpose. So we're talking about the polarity of a molecule, which is different than we've talked about before. Let me show you why. Before, we have talked about bond polarity. So we have talked about in a molecule like methane, bond polarity focuses on the attraction between two atoms, right? So within the molecule, we can focus on one of the bonds, the bond between hydrogen and carbon, and we can talk about how carbon is more electronegative, maybe, I think. Maybe I should check that information. Okay, yes, it is. Barely. It is, but barely. Okay. Anyway, carbon is more electronegative than hydrogen, so within that bond, the electrons inside that bond are going to be drawn towards carbon and away from hydrogen. When this difference is barely noticeable, as in carbon and hydrogen, the electrons don't get shifted very strongly, and the dipole of the bond is very weak. If we look at something where there's more of a drastic difference, like hydrogen and fluorine, for example, fluorine is much more electronegative than hydrogen, then the electrons get shifted very greatly towards fluorine, away from hydrogen, and the dipole is larger. That means that hydrogen is going to be partially positive, fluorine is going to be partially negative. The same would be true in the other bond we looked at. Hydrogen would be partially positive here. Carbon would be partially negative, but those partialies would be a lot less, right? They're almost equal in almost equal electronegativity. The bond doesn't get shifted. The hydrogen doesn't get a very big partial positive in that case. Whereas in the case of hydrogen fluoride, there's a really big difference in electronegativity. The electrons get shifted more greatly, and there's a really big partial charge, almost a complete charge on that hydrogen. So that's bond polarity. We have talked about that before. Now what we're going to talk about is molecular polarity. So what about the whole molecule? The whole molecule of methane, is that molecule polar or not? What about the whole molecule of hydrogen fluoride? Is that polar or not? So when the molecule is made up of two atoms, in the case of hydrogen fluoride, the bond dipole is the same as the molecular dipole, right? The bond dipole is the entire molecule. In the case of methane, however, that's not true. One bond dipole does not represent the whole molecule. And so we have to look at a couple other factors to figure out if the molecule is polar or not when there's more than one bond. Okay, so when we're talking about the dipole of the whole molecule, is the whole molecule polar or nonpolar? What we have to look at are a couple different things. We have to consider the bond dipole, all the bond dipoles that exist. And then we also have to look at the geometry of the molecule. So let me give you a couple examples here. First of all, let's look at water. Water is a pretty classic example. So first of all, we have to look at the bond dipoles within water. In order to do that, we have to draw the Lewis structure. So I'm going to draw the Lewis structure of water. All right. And then I'm going to look at the bond dipoles inside of them. Do the bonds have dipoles is the question. So in this case of water, yeah, the bonds have dipoles. Oxygen is more electronegative than hydrogen. The electrons are going to be pulled towards hydrogen, or towards oxygen. They're going to be pulled away from hydrogen. So yes, the bonds have dipoles. If we were to run into the case where the bonds do not have dipoles, then automatically our molecule isn't polar. Now, that's not a very common circumstance. In order for a bond to not have a dipole, you have to have the exact same atom on either side of the bond. So to have a non-polar molecule, number one, you would have to have no bond dipole. Now, if you just have a two-atom molecule, if you have a diatomic molecule, for example, like hydrogen, that's pretty easy to do. Hydrogen and hydrogen have the same electronegativities. There's no bond dipole. The molecule is not polar, right? And anything that is diatomic like that, oxygen, nitrogen, all of these are going to be nonpolar because there's no bond dipole. Now, that's harder to do if you have more than two atoms. You would have to have a molecule that is completely made up of the same atom, which is pretty unusual. Even if we were to attach a whole bunch of carbons to each other, those carbons would still be attached to hydrogens, right? And those hydrogens would now have a dipole when you compare it to the carbon. So to not have bond dipoles is pretty unusual outside of a diatomic molecule. Okay, so that's our first consideration. Do bond dipoles exist? And in most things that have more than two atoms, the answer is yes. Okay, the second thing we have to look at in the case of water is geometry. Okay, so in order to examine the geometry of the molecule, we have to look at the Vesper shape. So when we look at water, the central atom, oxygen, is going to have 4 regions of electrons around it, right? 4 effective domains. It has bond, and then lone pair. So 4 things around the central atom that are going to affect it. So in this case, we're going to have a tetrahedral molecule. You can think of it as a true tetrahedral where 2 of the things are taken up by lone pairs. Or you can think of water as a bent molecule. If you remember, anytime you have a tetrahedral arrangement that has 2 bonding pairs and 2 non-bonding pairs, you're going to have a bent molecule. So oxygen's bent, right? Either way you look at it, oxygen's bent. So if we look at the bond dipoles that exist within that geometry of water, it would look like one of these 2 circumstances, right? The question is, in the geometry, is do the bond dipoles cancel each other out? Do the vectors, okay, a vector is a directional force. So a dipole is a vector because a dipole is a force, right? The electrons are moving in a certain direction and it's directional. They're moving in a certain direction. So do the vectors reduce each other? So let's take a look. Let's explore that a little bit. Do the vectors reduce each other out? Do they cancel each other out? So this is the case of the tug of war, right? If we have vectors that are equal and opposite, either pushing each other or pulling each other away, if they're in equal and opposite directions, you know, that center is not going to move. And you can think of that as a tug of war. If we have 2 ropes and they're being pulled in the opposite direction, perfectly opposite, perfectly equal amount, the middle of that rope isn't going to move. If one of them's bigger than the other one, on the other hand, the center of that rope is going to move. So the question is, do the vectors cancel each other out? Now, you can think of this, you can kind of like spatially reason your way through this, right? So think about it as ropes. If we were to tie a rope to the oxygen from either direction, or like you have two football teams, I don't know, and they're pushing at this angle of slightly smaller than 109.5, right? They're pushing at that angle with equal force. Is that center going to move? Yeah, it is. That center is going to move a little bit. And so you have these two vectors that don't cancel each other out. You can think about it like that. The other way you could think about it is in terms of symmetry. Do you have symmetry? If they're perfectly symmetrical, right, they're equal and they're symmetrical, then they are going to cancel each other. If they're not equal and symmetrical, then they're not going to cancel each other out. So in this case, these two are not going to be pushing each other in equal directions. They're going to be pushing each other in an angle, and they're not going to cancel each other out. So we will have an overall dipole for this molecule. We'll have an overall force. So these two vectors are going to combine, and they're going to create an overall force. Now, let me show you how you would do this mathematically. When you get into physics, if you take a class in physics, you're going to deal with vectors because a lot of forces are directional. And anytime you have a directional force, you have a vector, and the vectors can build on each other. So what you would do mathematically is something like this. Okay, so here's my grid. Here's my X, and here's my Y, right? Okay, so if we have these two forces, this would be better on graph paper. Okay, but let me just draw in some graph paper here real fast. Something like that, okay? Let me make my forces a little bit better. Here's one force, or one dipole. Here's my other dipole. Okay, so you can see that they're both 2 over 2 up, right? Well, you can take these forces and you can rearrange them. So if I go, my graph paper needed to be bigger. Darn it all. Okay. All right, here I have graph paper again. All right, so if I take these and I go 2 over 2 up, here's my first dipole. And now I'm going to stack them on top of each other. I'm going to take the other one, go 2 over 2 up, right? And then if I go from my origin, from where I started to where I ended, if that is not in the same place, I am going to get an overall force. If my origin and my endpoint are in the same place, however, then I would get no dipole. Let me give you an example of that. If I had one that went over and up in this direction, and then a second one that went over and down in the opposite direction, notice how my origin and my ending point are in the same place. Those two vectors cancel each other out. The first two vectors that I drew, though, that look something like, where's my camera? Something like this. Okay, those two vectors don't cancel each other out. They have an overall vector that forms. Okay, so this is what we're talking about when we talk about symmetry. If they're symmetrical, if they're equal and opposite, they're going to cancel each other out. If they're not equal and opposite, they're actually going to build on one another and end in a resulting force, a resultant force. Okay, so a lot of words to explain the concept. In order for something to be polar, you must have bond dipoles, and B, those bond dipoles they cannot be equal and opposite, right? If those two things are true, if you have bond dipoles and they don't cancel each other out, your overall molecule will be polar. If either of those things are not true, though, let's say you don't have bond dipoles, then you will have a nonpolar molecule. Let's say you have bond dipoles, but they cancel each other out. You will have a nonpolar molecule. Okay, so that's how we sort polar versus nonpolar. So let me give you a couple more examples of that, and then we'll deal with a couple examples in class as well. So for something like ammonia, we want to know, is ammonia a polar molecule or a nonpolar molecule? So first, we have to draw the Lewis dot structure. Okay. Second of all, I have to consider, do I have bond dipoles? Well, nitrogen and hydrogen are not the same atom. There will be a difference in electronegativity. I will have bond dipoles. Okay. Third of all, I have to consider, are those bond dipoles going to be symmetrical and therefore cancel each other out? So then I have to look at the VSEPR structure. So nitrogen, around nitrogen, I have 4 effective pairs, right? 3 bonding pairs and a lone pair. So this is going to be a tetrahedral. And the 3 bonding pairs, or the 3 dipoles, are going to be on the bottom, and they're all going to be pointing up at nitrogen. So are they going to cancel each other out? Are they equal? Yes. Are they opposite? No, they are not. And so these are not going to cancel each other out. I will have an overall resulting force, which is going to be my molecular dipole. And this molecule will be polar. So notice the difference between bond dipoles, which are in purple, and between 2 atoms, and molecular dipole, which is in red, which is a combination of the bond dipoles. It's over the whole molecule. Let me give you another example. How about BH3? If I have BH3, okay, so first of all, I want to draw the Lewis structure. Second of all, I want to consider, do I have dipoles? And I do have dipoles. I know that hydrogen and boron are different elements. They're going to have different electronegativity. I'm not 100% sure which one's going to be more electronegative. Let's pretend hydrogen is more electronegative than boron. Either way, though. Okay. Next, I want to consider the geometry. So around the central atom, I have 3 effective pairs, 3 bonding pairs. And so this is going to be a trigonal planar molecule, which is going to look exactly how I have it written. It's going to be trigonal, pulling in 3 directions and in one plane. Is this a symmetrical molecule? Yes, it is. The dipoles are equal and opposite. If I have 3 ropes attached and those 3 ropes are pulling in these 3 directions, my center is not going to move. This is a nonpolar molecule. Okay, so we'll do a little bit of practice with that in class. As you work with that, you're going to pick that up. The trickiest ones to see are the tetrahedral ones. If you look at a tetrahedral molecule like methane, for example, methane is tetrahedral. It looks like this. Right? So the symmetry is hard to see. We're definitely going to have dipoles here. Right? Something like that. All 4 dipoles are equal. Now, are they opposite? I mean, they're not obviously opposite, but again, if you put all of these dipoles together, they're actually going to trace you back to your origin. It's hard to see, but the molecule is very symmetrical. So that's just the one trick to know. If you have a VSEPR shape you have all bonds, you have no lone pairs, and all the bonds are the same, the bonds are going to cancel out. And the bond dipoles are going to cancel out, and you will get a nonpolar molecule. So that goes for every single shape, whether it's easily seen or not. That's going to be true. So keep that thought in your back pocket. Try a couple of these. We'll try a couple together in class, and then we can talk through some of these that are a little bit less obvious. Okay, so that really brings us to our very final concept of bonding. And our last concept of bonding is the difference between atomic orbitals and molecular orbitals. So we've talked about atomic orbitals, right? If I give you an atom, you should be able to tell me all of the atomic orbitals that exist within that. Like, let's take sulfur, for example. If we're talking about sulfur, you can write the electron configuration for sulfur. 1s2, 2s2, 2p6, 3s2, 3p3, something like that. 4? Something like that. 4. It's 4. Okay. 3p4. Okay, so this describes all the atomic orbitals in sulfur. If we look at sulfur from a 3D perspective, we will see it has a 1s, it has a 2s, it has 2px, 2py, 2pz. Let's do the 1s in a different color so you can see it. It's going to have a 3s. It's going to have a 3px, a 3py, a 3pz. Those are all the atomic orbitals in sulfur that contain electrons. We could look at the same thing from an energy diagram standpoint, right? So 1s, 2s, 2p, 3s, 3p. Sulfur is going to have 16 electrons. So I can fill this in with electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So all of these orbitals for the atom of sulfur are going to have electrons in them. We're going to use the quantum mechanical model to describe the atomic orbitals of sulfur. Well, when sulfur bonds with something, it's no longer an atom. It's now a molecule. So our molecular orbitals that contain the bonding electrons, or the electrons that exist as lone pairs, those non-bonding electrons, are those molecular orbitals the same as atomic orbitals, or are they different than atomic orbitals? So that's really the last concept we have to talk about in bonding, is what do those molecular orbitals look like? And this really brings us to a couple big topics. Okay, so first of all, this is called the valence bond theory. Second of all, it's going to lead us to something called hybridization. And third of all, we're going to be able to describe these bonds as sigma bonds or pi bonds. And as we describe the molecular orbitals, and we describe the electrons inside them, and we describe the bonds that happen, it's going to enable us to talk about a couple effects that come out of this. One of those, which is magnetism, which is kind of cool. So, shall we get going? Okay, this is probably going to take us a little bit of time. And this is probably the weirdest, most abstract stuff we're going to get into for this whole year. So when you kind of get confused and you're feeling a little bit lost, come back to this idea of this is going to tie into describing orbitals of molecules. Okay, here we go. All right. So, valence bond orbitals. So we start with this idea of bonding in a hydrogen model. We're going to look at two different models and compare them. So what does this look like when hydrogen bonds with hydrogen? What does this look like when hydrogen bonds with chlorine? So let's start with hydrogen bonding with hydrogen. First of all, we're going to look at each hydrogen and the atomic orbitals for each of these hydrogens. So each hydrogen contains one electron, and that one electron is going to be found in the 1s orbital. So the 1s orbital is going to be a sphere. It's going to be kind of a small sphere, right? It's going to be a sphere. So when hydrogen bonds with hydrogen, we can draw out the Lewis dot diagram for this, right? Each hydrogen has one valence electron. So we have two valence electrons. We're going to bond them to each other. That bond is going to be those two electrons, and we have no electrons left over. So this is our hydrogen Lewis dot diagram. So from this Lewis dot diagram, what we can see is that these electrons are located in the middle, in between these two hydrogen atoms. So why does that happen? Well, we can look at the atomic orbitals first. So if each of these electrons for the atom of hydrogen is located inside its atomic orbital, inside its 1s orbital, those 1s orbitals are going to approach each other and overlap, right? So let me draw your attention down here to this graph. This is kind of a graph that we have seen a couple different times, but now we can relate it to the atomic orbitals of hydrogen. So if we have, in this case to the far right, if we have two hydrogen orbitals and they're kind of far apart from each other, there's no overlap, right? And the electron of one that's being shared with the electron of the other is not close enough to the nucleus, right? It's going to be an unstable system because these shared electrons are too far away from the thing they're attracted to. Now, likewise, if we look at a system on the other side of this, we can add one in here. Excuse me. Okay, if we take these orbitals and we overlap them too much, like so, okay, we overlap them a lot. We'll put in our nuclei here. Okay, we overlap them too much. Well, the forces of repulsion are going to start to take over. So the nuclei that are in each atom, they're too close to each other now. These two protons that are in the middle of each of our atomic orbital, they get too close to each other. The protons are going to repel, and we're going to be at an unstable, high energy system. And so that would be this case on the far left. So this case right here, you can see that has the lowest potential energy. This is like your happy distance. So there's some overlap that happens. The electrons that are being shared can get close to both nuclei, but the two nuclei aren't too close to each other where it's causing this repulsion, right? So we have atoms approaching each other. We have this happy overlap region, and then we have this stable bond that occurs. So when we have a hydrogen molecule, that bond is going to be formed from a 1s overlap, right? We can look at this in a chlorine bond as well. It looks slightly different in a chlorine bond, but it still works. So if we look at this case in terms of chlorine, okay, chlorine, the atom of chlorine is a little bit more complicated than the atom of hydrogen, right? If we write out the electron configuration from chlorine, we can see why. 1s2, 2s2, 2p6, 3s2, 3p5, right? If we're looking at chlorine, which is here, chlorine has 17 electrons, so it needs a lot more atomic orbitals in order to support these. So the valence electrons that are bonding in chlorine are coming from a 3p orbital. Now, a 3p orbital isn't a sphere anymore. A 3p orbital is a dumbbell. So if we assume that the valence electron, the very last electron that's put into that valence shell, is going to do the bonding, well, we still can have an overlap from a chlorine molecule to another chlorine molecule, but that overlap is going to happen from the P shell. So we get a P shell from one chlorine overlapping with the P shell from the other chlorine. Again, we're going to have the same thing happen. If they're too far apart, the electrons aren't close enough to the nucleus they're being shared with. If the dumbbells, if the orbitals are too close, then you're going to get the nuclei from these protons of chlorine too close to each other. They're going to repel each other away, right? So we want this happy little overlap of the two P shells. And in that overlap is where the electrons are going to be localized, where they're going to be located, right? And we're going to get a bond. So here's the two electrons are going to exist in this overlap region. So it works out, right? So far, so good. Now, what happens if we look at hydrogen bonding with a chlorine? Okay, so a similar idea. Let's take the atomic orbitals and let's overlap them. So for hydrogen, we have an atomic orbital of 1s. For chlorine, we're going to have an atomic orbital of 3p. Okay, so it's going to be a lot bigger than the 1s orbital. It's going to be a different shape than that 1s orbital. But when those two overlap, I didn't draw that overlap perfectly, but when those two overlap, okay, that's going to be where the bond is formed. Now, this is the atomic orbital theory, right? The atomic orbital theory of bonding, that atomic orbitals have to overlap. Where that overlap occurs is where the shared electrons are going to exist, and that's what causes a bond. But all of a sudden, we have a problem. We didn't have a problem with diatomic hydrogen. Okay, the atomic orbital theory worked very nicely. We didn't have a problem with diatomic chlorine. The atomic orbital theory of bonding worked very nicely. But all of a sudden, we have a problem here for hydrogen chloride, hydrochloric acid. We have an issue here. Can you look at this model and tell me what the issue is? This would be a good time to pause the video if you want to think about this a little bit more. Okay, and here's the issue, is when we measure the distances between the nucleus of hydrogen and the nucleus of chlorine, they are at vastly different distances from each other, right? The nucleus of hydrogen is much closer to where these electrons exist. The nucleus of chlorine is much farther away from where these bonding electrons are going to exist. We have a lopsided molecule, and that's a problem because when we observe hydrogen chloride, hydrochloric acid, or any diatomic molecule, we don't have lopsided molecules. The electrons, actually, they get pulled closer to chlorine because chlorine is the more electronegative element. They're not going to be pulled more closely to hydrogen. And so here's where our atomic orbital theory breaks down. Okay, and so what happens when a model breaks down? Well, we look for evidence that contradicts our model. We have found that, right? And then we have to come up with a new model or change our current model in order to better predict what actually happens, right? So in this case, this is why we need to start looking at a different model. And that different model is going to be the model of molecular orbitals. or the valence bond theory that describes molecular orbitals. Okay, so far we've talked about, we've reviewed atomic orbitals. We've talked about what it would look like if we used the theory of atomic orbitals to describe bonding. And we've found a couple problems that occur when we use the atomic orbitals to describe bonding. So now what we're going to talk about is a new theory of molecular orbitals. All right, so here we go. Okay, I can show you, actually, before we get into molecular orbitals, let me show you another model with CH4 that would also cause problems. So if we are going to talk about methane, and we're going to talk about the atomic orbitals of methane, okay, so we have carbon, 1s2, 2s2, 2p3 or 4, 2p2. And then we have hydrogen, which is just a 1s1, right? So we have the 2p orbital of carbon overlapping with the 1s orbital of hydrogen. And then we have that again. Now, we have talked about the p orbitals. Remember, there's 3p orbitals, and what are they? 3px, 3py, 3pz. Okay, so I've drawn 3px. Here's 3py with another hydrogen. Remember, it's CH4, right? So I have to use 4 hydrogens. Okay. Now, Z is going to come out at me. And so I'm going to draw it as if it's on an angle. Something like that. Okay, but here's the question. First of all, I've only used 3 hydrogens, but even here, just addressing these first 3 hydrogens, I already have an issue, right? What's the angle between X and Y, the X and Y axis? What's that angle? It's 90, right? And so all of a sudden, I have my first 2 bonds between my first 2 hydrogens, and they're at 90 degrees to each other. And that's a problem. We know that methane is a tetrahedral molecule. We know that the bond angles in methane are going to be 109.5, not 90. So here's a problem. Here's a problem number 1 with using atomic orbitals to describe bonding in methane. Problem number 2 is, where does that third hydrogen or that 4th hydrogen connect to? It connects to carbon's other valence orbital, which is the 2s. So you have a 2s orbital here, and s's are slightly smaller than p's. And so you have that 2s orbital bonding to another hydrogen somewhere around there. Who knows what angle that would be? But the distance of that bond would be different than the distance of the bond using the p orbital of carbon. So a 2p, 1s overlap, 2p, 1s overlap is going to be a different length than a 2s, 1s overlap, right? So problem number 2, bond lengths are going to be different. So again, we see issues with using atomic orbitals to describe molecular bonding. Okay, so how does our theory change? Here's how it changes. Okay, so I'm going to describe this change to you using, let's go ahead and use BF2. We'll get to describing methane again. I'll walk you through methane, but let's start by talking about molecular orbitals using BF2. Okay, so here we go. Here's our molecule we're going to talk about. So boron in the ground state, right? Boron is going to have 5 electrons. So here's the 1s, 2s, 2p. Okay, 1, 2, 3, 4, 5. There's boron's ground state. Now, in this case, we only have one unpaired electron, right? So boron, as it stands atomically, is only really prepared to make one bond. And so we're going to promote electrons. Notice that the core electrons are going to stay the same, but one of these electrons in the valence energy level is going to get promoted up. Okay, and there I have 3 electrons now that are ready to bond if I need them to bond. Okay. Now, what happens is I have an electron in the s orbital of boron and an electron in the p orbital of boron. And we just looked at the case of methane, where if these 2 orbitals were to bond with fluorine's orbitals, right? Fluorine is going to use a p orbital to bond. Okay, so if I bond fluorine's p orbital to boron's s, and I bond fluorine's p orbital to boron's s, those are going to give me different bond lengths, right? If I take a fluorine's p orbital and I bond it to boron's s orbital versus fluorine's p orbital to boron's p orbital, I'm going to get 2 different bond lengths, which is what I'm trying to avoid. And so these orbitals, this s and p orbital that are about to bond with fluorine, we say that they hybridize. So they kind of merge their energies together and they come up with a different shape at a different angle. Okay, so I had 2 orbitals, right? S and P. I'm going to hybridize those and get 2 new orbitals. Since I used an S and a P to hybridize them, the new orbital that I get out is going to be an sp orbital. And since I hybridized 2 orbitals, an S and a P, I'm going to get 2 orbitals out. sp, sp. So notice I get 2 orbitals out. Here's one of the SPs. Here's another of the SPs. Notice it's a different shape, and those SPs are going to overlap at a different angle to one another. Notice that if I had 3 p orbitals, they would be x, y, z, right? 90 degrees to each other. If I have an sp overlap, they're going to be 180 degrees overlap. Okay, so I take the electrons I have, I promote the electrons to enable them to form bonds, and then I take the 2 orbitals that need to form bonds with my 2 fluorines, right? I'm going to hybridize them. I get a new shape and a new angle. So this is what I call a molecular orbital. An sp orbital is a molecular orbital. It's an s and a p hybridized together to get 2 sp or molecular orbitals. The atomic orbitals are s and p. The molecular orbitals are sp and sp. Now, this fixes a lot of our problems, right? So notice that if I have my sp orbital, which is this, okay, let me take this one and move it up here so I can show you. I have an sp orbital from boron, and I have my second sp orbital from boron. Now those 2 sp hybridized into sp and sp are able to bond with fluorine's f orbital. No, p orbital, sorry, fluorine's p orbital. Okay, so here's fluorine's p orbital. And it's overlapping with boron's sp orbital. And notice that I get a molecule that is consistent with the Lewis dot structure and the Vesper structure that I would have predicted, right? Okay, I actually want to work with beryllium. Beryllium fluoride. So that would have 2, and that would have 2 times 7, which is 14. That would give me 16. Okay, so beryllium, fluorine, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There we go. All right. And remember, beryllium is okay having less than an octet. So notice that my central atom has 2 things around it, 2 electron regions that are going to repel. And that would give me 180 degrees, which is what my molecular orbital, my hybridized orbitals are going to predict. Okay, so I've just walked you through the hybridized orbital theory once. I've walked you through it for SP. You should be able to tell me at this point in time what problems arise from using atomic orbitals to describe bonding, why we need this new theory of molecular orbitals. You probably won't be able to describe sp orbitals to me yet. Maybe you can tell me a couple characteristics that they have based on what we just went over. But we're going to go through this again next class with other examples that have 3 central atoms or 3 electron domains around the central atoms, and then again with 4. And as we go through this over and over, it's going to make more sense. I promise. So if you're feeling a little confused and like this is a crazy theory right now, I feel you. It kind of is. Okay. But then we're going to go over it again and again, and it's going to feel better the more we go over it. So trust me on that. Write down your questions. Bring your questions to class. Let me know. We'll talk through them. I swear you're going to feel better about this in a little bit. So see you in class.